Understanding how designed structures interface with bodies of water is very important for creating safe and efficient buildings and machines. Floating structures, such as oil rigs, need to remain stable even in turbulent ocean conditions. Stability of a floating structure is influenced by its height and center of gravity. Studying the relationship between these variables is integral to creating optimal designs.
The center of gravity is the average position of the weight of an object. At this location, a force can be applied without a resultant angular acceleration. The center of buoyancy is the center of gravity of the displaced fluid. Metacentric height is the distance between the center of gravity of an object and its metacenter and represents the body's resistance against overturning. Stable masses have positive metacentric heights, meaning that the center of rotation of the body is above the center of gravity. Unstable masses have negative metacentric heights, meaning that the center of rotation is below the center of gravity. Larger metacentric heights lead to a greater body stability. Therefore, metacentric height is a measure of the stability of an object.
The equipment utilized is the H2 Mark II equipment for determining metacentric height and stability and magnets for manipulating the distribution of mass. The hull was placed in a larger rectangular container filled with water to a height where there was no risk of collision between the container and the hull. The center of mass is measured using the center line hanger. After this, magnets were attached to the hull in varying configurations. The hull was trimmed in order for only the adjustable mass to influence the stability of the vessel. The adjustable mass was then attached to the sail and the angle of tilt recorded. This was repeated for the positions of interest until sufficient data was collected.
I'll go 4.
After acquiring data on the position of the adjustable mass and angle of rotation of the hull for all the trials, we started to analyze the data. For each of the different trials, we graphed the measured rotation converted to radians against the distance of the movable mass from the midpoint. From these graphs, we get a slope for each of the rows the mass is placed on. Then using these slopes, we could calculate the metacentric heights for each row on all the trials. Finally, these metacentric heights are graphed against the center of gravity for each row. From this, the y-intercept of each different trial's trend line is the calculated metacentric position relative to the center of buoyancy.
Our findings from this experiment are that distribution of mass does impact stability. However, we found that the distribution of masses along a plane on the perpendicular axis seems to have little to no impact on the stability of the ship. With the hull floating in water, the clinometer would sway ever so slightly unless given a long amount of time to stabilize. Due to this sway, there is a high probability that some data points are slightly off from the true values for that orientation. Other such sources of error could include the trimming mass not being completely in the correct position, causing the assembly to not have a perfectly even keel. Another possible source of error is that the adjustable mass was not fully in the slot for each horizontal position.